Hi, Zach. Here we go with number 92. There are three structures to make here. You have to predict the structure and the bond angle. The first step to doing that, of course, is to figure out how many things are stuck to the central atom. So that would require something like a Lewis structure. So let me draw the Lewis structure for PCl3, and then we can figure out the geometry from there. You put the first atom in the middle, and you put the rest of the atoms around that first atom, and then you make sure everybody has an octet of electrons. Of course, when you count for the octet, the line is 2 electrons. So everyone now has 8 electrons around them, and now I must make sure that I have used only the number of valence electrons that are available in these atoms. Phosphorus is in group number 5A, so it has 5 valence electrons. Chlorine is in group number 7A, so 7A, on some periodic tables it's called 17, but that's all right. It has 7 valence electrons, so there are 3 of them. So that's 26 valence electrons. Oops, 26 electrons total. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So that checks out. This is a good Lewis structure. I can just see by inspection that all the formal charges will be 0 because phosphorus, having 5 valence electrons, makes 3 bonds for a formal charge of 0, because 8, the octet, minus 5, number of valence electrons, is 3. 1, 2, 3, 3 bonds. Chlorine, in the same way, makes only 1 bond. 8 minus 7 is 1. 1, 1, 1. So there are no formal charges here, so this is a very good Lewis structure. Now, let's look at how many things are hanging off of the central atom. 1, 2, 3, 4. 4 things hanging off of the central atom. So that means those 4 things will be arranged in a tetrahedral manner. Okay? Because anytime you have 4 things, it doesn't matter what those 4 things are. Anytime you have 4 things hanging off of the central atom, it will be tetrahedral. That's the best way to get the things as far apart from each other as possible. The natural angle for the tetrahedron is 104 degrees, the separation between each thing. So, is this the bond angle? No, because one of those things, now we have to consider what those things are. 2 of those things are bonds. 3 of those things are bonds. One of those things is a lone pair. The lone pair takes up much more space than a chemical bond. So the lone pair will be pushing these chemical bonds, squeezing them together. So that means the angle between the lone pair and the chemical bonds will be higher than 109.4. But the bond angle, which is the angle between the bonds, that's going to be lower. So that's going to be about 107. Where am I getting this? I think you know already. I'll say it anyways. I'm getting this from page 370 in your textbook, pages 370 and 371. There are little tables and little figures on pages 370 and 371 that show the angles there. On page 370, there is an NH3 molecule in the table at the center of the page. Bond angle is 107 degrees. PCl3 is very similar to NH3 in its geometry and in its Lewis structure also. So there it is. Now I'll get a new page for you. Okay, new page. And let me do the SCl2. Oh, I'm sorry. I forgot to say the geometry for that PCl3. Of course, the geometry is tetrahedral for everything that's hanging off of PCl3. But that is not the molecular geometry, because the molecular geometry always ignores the lone pair. So the molecular geometry is not tetrahedral. It is tetrahedral minus a leg, this leg. So the molecular geometry is pyramidal. Let's see. That word is on page 372. Your book calls it trigonal pyramidal. trigonal pyramidal. Okay, it's called trigonal pyramidal because a regular pyramid, it has a square base, you know, and then it has the point. It's like the Egyptian pyramids, right? But this pyramid has a triangular base. There it is, the triangular base, right? And then it's a pyramid on top. P is at the top of the pyramid. Okay, now I'll take you to the next page, and we'll do the next structure. These are kind of easy structures. This PCl3 and also part B, which is SCl2. Oh, actually, no, SCl2 is interesting. Part C is easy, SiF4. But anyways, let's do the interesting one, SCl2. Now, let me draw the Lewis structure right quick. Put the first atom in the center, dot, 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 dot. Give everybody an octet, right? And then I've got 6 electrons, valence electrons on the S, that's an S, and 7 on the chlorine. There's 2 of those, so 14 plus 6, that's 20 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh, it's easy. Huh. I didn't expect that to be easy. That's 20. So now, there are 4 things hanging off of this S. So that means the geometry of those 4 things is tetrahedral. But is that the molecular geometry? No, we have to figure this out. It's tetrahedral. So that's the overall geometry. But you know that the lone pairs take up more space. Take up a lot of space, okay? So ordinarily, a tetrahedron has the 109.4 degree angle. But here, these 2 lone pairs are going to be squeezing the CLs together. So the CLs are, so if there's a CL here and a CL here, the CLs, the bond angle is going to be something like 105 degrees, something less than 107. And why is that? That's because here we have 2 huge lone pairs squeezing the CLs together because they're taking up space. They're very repulsive because they're made of electrons only. There's no nucleus there at all. It's just a lone pair of electrons. Whereas these bonds, these are made of electrons and somebody's nucleus, chlorine's nucleus. And so these don't take up as much space, and they're not as repulsive to each other. So these guys are very repulsive. These lone pairs are very repulsive. So let me check the exact angle as given in your textbook on page 371 or 372. Okay, so there it is on page 372. It's this geometry is called V-shaped. Most textbooks call this the bent geometry. Your textbook calls it V-shaped or bent. Okay. Now let's look at the angle for that bent geometry. It's about 104.5. So the angle, I called it 105. Your book calls it 104.5. It's about 104.5, and you could see that angle on page 370 at the bottom in the water molecule drawing there. They have a drawing on page 370. Page 370, they have a water molecule. It's like this. OH2, H2O, and the angle there is 104.5. The water molecule has that bent geometry, or according to your book, that V-shaped geometry. Okay? So that was kind of interesting. The reason why I say it was interesting is because you would expect, without doing all this study, you would expect SCl2 to have the linear geometry, because there are 2 things, apparently, before you draw the Lewis structure, there are 2 things hanging off the S. You would expect them to be as far apart as possible, which would make the bond angle 180 degrees. But that kind of guesswork doesn't work here because there are lone pairs to consider, as you saw. Okay, I wonder if this method that I'm using is helpful to you, you know, this YouTube video. My idea is that you could just watch this on your phone while you do something else, you know. Okay, so SiF4, but I really want to make sure that you understand, because I am not with you, the only way for me to help you on your exam is to make sure that you understand the homework, and the labs. By the way, are there any labs this week? I really want you to get more points on those lab reports. I kind of want you to get an A here. I'm not sure if that's possible because of that thermodynamics exam, the low score there. Maybe an A minus, B plus, something. Okay, so this is SI F4. I have sketched the Lewis dot diagram there. Si is in the same group as, is it the same group as carbon? Yeah, so that's 4 valence electrons, and F is 7 valence electrons. There are 4 of these, so 28 plus 4, 32 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that's good, 32 valence electrons. No problems with these Lewis structures. Now this is tetrahedral, of course, because it has 4 things. Now these 4 things hanging on the Si, they are all atoms. And so the molecular geometry is also tetrahedral. And what is the bond angle for a tetrahedral thing? Here's a tetrahedral thing. Okay, so chemists really, when they want to draw something 3D, this is how they do it. They make a wedge here, showing something going out at you from the page, and they make this dotted line here, so showing something going into the page, and then they make another out of the plane of the page. So this is supposed to be tetrahedral, 109.5 degrees. Okay, so anyways, that's the bond angle. Hope this helps. Please let me know if this helps. We can do this type of work. I mean, you can order this type of work from me rather than a meeting or in addition to meeting. I prefer it to be in addition to meeting because I want to also have access to you to ask questions of you to see if I could tell if you understand this properly or not. But anyways, let me know if this has helped. Thanks.